don't need that. Okay, so let me continue what we were talking about last time. So we were talking about like the Converse proof of the channel quadratic theorem near the end, and we described and proved the Fano's inequality. Let's see if I can find it. So the Fano inequality, where is it? Oh yeah, that's the Fano inequality. Is basically we have a setup of a channel coding setup that have the output of the channel yn, and then the message coming in is the message to be coded as transmitted as m, and we have the conditional entropy of m given yn is less than this, and this is the final inequality. And PE here is the probability of error, the probability that we have a 1 year's transmission. And so we end like halfway, actually not even halfway, just beginning to show the converse proof. So it's a little bit messy here. I guess it's like, did I have anything here? Okay, let's restart here. So maybe we start with a new page. So the converse, what we're trying to show is that like if the probability of error is equal to 0 or going to 0, then the weight has to be kind of smaller than the capacity, basically what we want to show. And the weight here is basically like, because we use the channel n times, right? The weight will be the amount of information we send is hm over n, and it's just equal to, if we just use the equation for like the conditional entropy and mutual information, I can expand this hm as im yn plus hm given yn. And then like I can use, basically I have a what's that? Certainly forgot the name. Data processing inequality, yes. So because we have a Markov chain that we have m, the message coming in, go through an encoder, and then we have xn that is the encoder output and go for a channel, and then we have yn is like the output of the channel. So we have a Markov chain basically like m, xn, yn. So by data processing inequality, the mutual information between these two guys will be bigger than equal to the mutual information between these two guys. So therefore this will be less than equal to 1 over n I xn yn plus hm given yn. So and then of course I can expand this again in a different way. This will be like just hyn minus hyn given xn plus hm given yn. So, and then like I can, for this term here, I can expand that with a train rule. It's like equal to hyi xn yi minus 1 plus okay, yeah, just this guy is equal to this one here. Now then we can use the Markov inequality again. So basically, given xn here, let's see, actually yi would be just depend on like the incoming input to the channel, right? Because the channel is kind of memoryless. The output at the ith instance, like yi should only depend on the, or I should say, like given the current input, like xi, it should not depend on anything else, right? So therefore, like this should be just equal to hyi given xi. So therefore, like I have this is equal to 1 over n hyn minus sum over I hyi given xi plus hm given yn. And now, let's see. Now I can also expand this guy, right? This guy will be equal to hyi, or I can write it as a summation here. Hyi given yi minus 1. But using conditioning in reduces entropy, then each of these terms will be less than equal to hyi. So therefore, like this is less than equal to 1 over n h sum over I hyi minus I hyi given xi and plus this hm given yn. Okay, and then of course I can group these two terms together. This will be just sum over I, the mutual information between xi and yi here. And so therefore, like this is equal to this plus hm given yn. Now then we can use the Fano. If you remember what the Fano is saying, that like hm over yn is equal to 1 is less than equal to, this is actually less than equal to 1 over n I xi yi plus 1 plus p hm, I think. Yeah, something like that, right? Let me just make sure Fano, where's Fano? Yeah, Fano is here, yeah, that's right, right? So then of course I have 1 over n here. So 1 over n of this guy, this PE is is equal to 0, right? Assume that PE will approach 0, so these terms will be gone. So it's just 1 over n. So the whole thing is like will goes to 0 as n goes to infinity. So therefore, like this will just go to sum over I xi yi 1 over n as n goes to infinity. And of course, because the channel is kind of memoryless, your xi, y have the same statistics overall. This is just ixy here. So you're summing like n ixy here and dy 1 over n. That just got cancelled. So this is just equal to 1 over ixy. So that means that what we get eventually is the Converse proof is that R, so S of P is equal to 0. So you're going to stay on? Yeah. So PE is, as PE is going to be 0, we have R is less than equal to IXY. And of course IXY is like less than the capacity, because capacity is just equal to the maximum IXY, right? Maximum over the input distribution. So therefore, like this shows that like whenever the probability of error is equal to 0, the weight has to be less than the capacity. And this finished the Converse proof. And that's it for the converse proof. And now let's just like look at one example. Kind of let me just maybe open the new page here.
Someone speaking?
Oh, I don't think so.
I hear someone.
Maybe it's outside. I guess it's maybe I can. Yeah.
I hear.
Yeah. So okay, let's look at an example for. Let me find a new page here. Look at a color Gaussian channel. So color in the sense the channel is at different frequency, or you can think of different band do not have the same amount of noise. So for example, like I have a channel like this. Let's say this is the range I'm going to able to transmit something, but this is the noise level here. The noise level is lowest here at the mid band, maybe like then it's higher on these two sides, let's say. And
that is why always like convex like that.
No, it doesn't necessarily. I just arbitrarily put down something. Or maybe I can put like this, like whatever. Like this is
that's why I thought.
Yeah. And it's a kind of color channel. So intuitively, like one thing we kind of like simplify this thing is like we can kind of discretize this channel into like different frequency, right? And maybe like something like that, approximately. So it's a different frequency. This is like the noise level at different frequency. And intuitively, like what we are doing is we're supposed to do is we want to assign different kind of power at different band here. So at different band, we are going to
Power spectral density.
This is like a power spectral density, but of the noise power spectral density, basically, yes. And so then in the sense this is just an allocation problem, right? Because for each of the channel, remember that like if I have the capacity here, I assume this is a Gaussian channel, right? So therefore the capacity is just something like 1 per SNR, like I think it's like log 1 per SNR, something like that, right? So I guess I have 1/2 here, 1/2 log SNR. So then let's say I have this, as I mentioned, from a continuous allocation, I kind of simplify it into a discrete allocation. So let's say I have like noise power starting from like sigma 1 square up to like I have k band, big K, so many bands here, right? Sigma k square. Now the question is how I'm going to, actually this is not much kind of information theory problem, but it's more like a optimization problem. So we want to allocate power to each of this band here, and then the resulting basically the resulting amount of information we can sample these channels will be basically sum of them, right? So let's say if I assign power P1 to the first channel and Pk to the last channel and Pi in the immediate and so on, P1, P2 and so on, then the total amount of information I can sample is just log 1 plus Pk over sigma k square, right? So And let's say this k is like from this small k is from 1 to big K, something like. Okay, my big K and small k is quite similar. So then there will be some constraint here. So we want to maximize this, right? So therefore I say it's an allocation problem. It's also actually just an optimization problem. And the variables here is basically just all this p, right? These are the variables, by the way. So what subject is a
That's the ratio.
what?
That is the ratio between capacity per bandwidth.
Which you're saying what? Which one?
This is capacity per bandwidth ratio. This is actually capacity per bandwidth because there is W in here before.
Oh no. That one is like okay.
Channel.
Yeah, you have that yeah here okay. Let's forget that one. We just simplify this here, because I be assuming okay here will be like K parallel channel. You can think of that W is kind of like the K here, right? Because you have K of them, right? But now, each of the channel here like can have different noise power, so you're not going to assign the same noise power there. I mean same power there. They have different noise power, so you're going to assign different signal power there as well. Yeah, so therefore it won't be like just W over 2 log 1 plus P over sigma squares, let's say, because each of them is different. Yeah, so
for K.
So you yeah your K yeah K is essentially W there. So yes, then we want to maximize this for different power to be allocated there. We have some constraint here, right? This is we want to maximize that, but some constraint. First of all, like all this power has to be positive, right? Pi, let's say, it's all has to be greater than or equal to 0. Okay? And then like let's say we have a total power constraint. If like it's unlimited, then this, I mean, of course I can assign pk all to infinity, then this will be unbounded. So let's say I have a maximum total power. This is a maximum total power, and let's say this, so therefore like sum over all peak, maybe I'll use pi, I equal to 1 to k will be less than or equal to p. So this is like the constraint here. Let's say subject to these constraints here. So we have an optimization problem like this. So let's try to solve this one. So then again, like it's just use some of this kind of like Lagrange multiplier and KKT conditions. So let us just write down all the KKT conditions. First of all, like we can absorb the constraint into this optimization problem, right? So therefore, like we should, for this one, by the way, for this one here, there's only one constraint. We can have a Lagrange multiplier mu here, let's say. And here be careful, like we actually have like k constraint here, right? For each of these powers bigger than k. And let's say, let's use the lambda I as the Lagrange multipliers. So then if I absorb the constraints there, I have like 1/2 k equal to 1, or let's use I, because my big K and small k, well, it's almost the same. Log 1 plus pi sigma I square and plus sum over 1 to k lambda I pi. That's basically the constraint here, absorbed to here, and then minus mu sum over I equal to 1 k pi minus p. So something like that. So I can try to, yeah.
Where it come from lambda? Yeah.
Lambda is here.
Yeah. What is it?
That's the Lagrange multiplier.
Okay.
Yeah, this the same thing as mu here. So we absorb the constraint into here, right? So we have just the constraint with this mu here, introduce the Lagrange multiplier for this guy. And here is essentially I have like k different constraint, right? And each of the constraint I have a lambda I as the Lagrange multiplier. Or you can think of this as like pi minus 0 or something like that. But because it's like 0, so didn't write it down. So and then like if you can think of this as a mini-max problem now. Like you have mean of over the Lagrange multiplier, and then maximum over the pk here. But if we can directly use the KKT conditions. Then the KKT conditions will be like I want to take the partial derivative of this over the original variables and set it to 0. Basically, the gradient over p should be equal to 0 for this guy here, and also for the Lagrange multipliers, mu lambda 1 up to lambda k all has to be bigger than equal to 0. And be careful, like one of the constraint here on this side is less than equal than p, right? This one is larger than equal to 0. So therefore, there's a sign difference here. Like I have plus sign here and minus sign here. So I can all use plus sign, but then this will be more complicated. Then I have mu has to be less than equal to 0 instead of larger than or equal to 0. I also need to have the original constraint for p1 up to pk should be bigger than equal to 0. And then also the original constraint like pi is the total power has to be less than equal to p. And I have the complementary slackless condition. Basically, this thing as a whole is equal to 0, and this thing as a whole is equal to 0. So there's a mu sum over I equal to 1. Okay, pi minus p equal to 0, and sum over I equal to 1. Oh, sorry, no. And also like lambda I pi is equal to 0 for all I here. So that's all the KKT condition. KKT. And now from the first equation here, if I take partial derivative over pi, then let's see, the first term, I have pi here, I have pi here, so I have a mu here, I have a lambda I here, basically I have lambda I plus lambda I minus mu here, this one is equal to 0. This part is more complicated, but it's a 1 over 1 plus pi over sigma I square, and there's a 1/2 here, I think, and times 1 over sigma I square, something like that. So therefore, like what we have is basically P1 over, let's see, 1 over pi plus sigma I square is equal to, let's see, sigma I square is equal to mu minus lambda I, again for time 2, yeah, something like that.
Sigma.
No, where times sigma? There's no sigma here.
Then sigma.
No, that got, okay, this sigma I square times this, that got cancelled, right? The sigma I square times it, that's our sigma I square. That's why I have pi plus sigma I square here. Yeah. And then therefore this get like pi plus sigma I square is equal to 1 over 2 mu minus lambda I, something like that. Now let's see. Now since I have this complementary slackness condition here, lambda pi is equal to 0, then let's say like if pi is bigger than 0, for the band there, we're actually going to have positive power. Then lambda will be equal to 0, eh? Then lambda I is equal to 0. Then in that case, this I can ignore that, and I have like pi plus sigma I squared is just equal to 1 over 2 mu.
That's right.
Actually, if you look at that, like, that means the mu has to be positive, right? Because the left-hand side power and sigma I squared is positive, so this has to be positive. And then, like, if we look at sum over pk, then pi, or like sum over pi, then I 1 to k, this one is equal to p. That means that
That's sum of all for all then.
let's see.
Okay.
Actually, I don't. Of course, this is the constraint we need anyway. I don't know why I'm writing it here. So this is the constraint we need. But just look at this one. Already we have sufficient information to claim what pi is supposed to be. Something like if you add this noise and the power together, it should be a constant basically. Right? You see that? So that means that if I have like a distribution, for example, like that. So this is the noise power, let's say. Then if I have, let's say, what I want to say, if let's say if P1 is this one, this is, let's say, this is sigma 1 square, then Pn plus sigma 1 square should be equal to P2 plus sigma 2 square, right? So P2 should be this side, that much, right? If this much is P1, P2 should be this much, right? And because when they add together, it's a constant.
Constant?
Yeah, you look at this one here. Pi plus sigma I squared is equal to 1 over 2 mu, right?
Oh, yeah,
Right? It's
right.
just a constant.
Always constant.
Yeah, mu is something, but it's a constant with respect to the I, right? With respect to each band, right? So therefore, like, let's say if I have P1 plus sigma 1 squared is here, then for the rest of P2, P3, P4 will be basically is just equal to this height here, P3 is just equal to this height here, and P4 this height here, and so on. So there's a name for that. It's like something like people describe it as water filling. So it's like you have some kind of like I don't know, an irregular shape of bowl, maybe, like, then you fill water into that way. And then like all this power level has to be like fill up, like when the power added with the noise has to be constant.
So the mu is always given at there?
Actually, the mu, no, actually, yeah, you can say that, but not completely right, because the mu is actually related to this P, right?
The mu, sorry?
Mu is actually related to this total power P here.
How?
Because the mu, like you say, like this add together is equal to 1 over 2 mu, and therefore like this is 1 over 2 mu, right?
Oh yeah, that's right.
Yeah, and what is the power? The power is actually the total wall area here, right?
Oh, that's right.
Yeah. So therefore, if you have a more power, then your 1 over 2 mu will be bigger.
Yeah, that's right.
Yeah. So then the question is then, like, okay, how about if I continue to decrease the power? Let's say if my power reduce, like this is the total power, like this, right? This is the total power, and let's say now, and let's say this volume is, this area is like, what should I say? Yeah, this area is P. Yeah, the area is P. And let's say if I have this area kind of reduce, if we reduce, this water level will go down, right?
That's right.
It will go down, but it will go down up to the point. Let me just write better.
To the higher one.
Yeah, to the higher one here. So the question is, like, when it touched the highest one, then what should we do? Right? When we touch the highest one, when we continue to decrease the power, what will happen?
Yeah.
For example, here, if I continue, now at this point, like, then there will be no power for this first guy and this last guy here, right?
Yes,
So, but how about I continue to reduce the power?
Continue to reduce the power. Power will be 0.
No, not just, it's not just, okay, this 2 is 0, P1 and let's say 2, 3, 4, 5, like P5 and P1 will be 0 now.
Zero.
But like if I continue to decrease the total power,
Yeah.
then
Still has Pi not 0.
so we can, the water level will continue to go down, but then because P has to be positive, right? So this one cannot go negative. So for example, if my water level go down to here, then I need to have this sigma 1 potential. So I should have like sigma 1 squared plus P1 should be equal to 1 over 2 mu, right? Now 1 over 2 mu is here, right?
Yes.
But if I need to have sigma 1 squared plus P1 equal to 1 over 2 mu, then P1 has to be negative, right? But P1 cannot be negative, and this is okay because you have this here. Remember why we have this is basically we claim that like when Pi is positive, then we have lambda I is equal to 0, right? That's from the complementary slackness here. So now if Pi is allowed to be 0, then lambda I can be anything. Actually, lambda I can be positive.
Yeah.
So lambda I can be positive. Now this, in this case, lambda 1, actually lambda 1 will come back here. Lambda 1 now is no longer equal to 0. And actually what will happen is that we will have lambda 1 here is not equal to 0. And this is equal to 1 over 2 mu here. But this level here is equal to 1 over 2 mu minus lambda 1. And this exactly gives us when P1 is equal to 0 here. So therefore, in summary, what is going on is that if we continue to reduce the water level, let me use another color here. If I continue to reduce the water level, what's going on? Like for the first one, the power is still equal to 0. But the level will go down, then for the west, we'll have the power. Now P2 is equal to this height here, this height here. Yeah. So it's a little bit messy to draw. So, but that's basically the solution for the parallel Gaussian channel. Yeah.
What is the conclusion?
The conclusion is we want to have an allocation. Oh, okay. What you have, like if you remember, we have a formula that like you just mentioned, W21 plus SNR or something, right?
Yes.
That's the case for white Gaussian channel. So that's when like you have kind of a band, like all the noise power is the same. It's like the power density is the same for the noise power density.
Yeah.
But now if I have a
Color.
more realistic, color one, as we draw like a shape like that, whatever, then what's
Capacity.
then the capacity won't be equal to this, because at each different powers, the optimum way to allocate the power should be different. And we just show that like the optimum way will be if you have so much power, and the power is not defined, but essentially is equal to the kind of like the water above this thing here, and the power for each of the channel is basically the depth from the water surface to the fall of the noise. And then once you have this allocation, then you find the PI, right, for each of these guys, right? And then the capacity then will be like sum over 1 plus Pi over sigma I square, and this is the optimum Pi basically. 1 equal to 1 to K something, or like if you like you can use W, something like that. So this is the capacity basically. Yeah.
So with the water filling and down, so mean that if the power is decreased, if the power of Pi is decreased, and then what's the capacity in there? Still like that?
No, if your P decrease, if your P decrease, your Pi star here will different, right? Because if your P decrease, you have the Pi star. So essentially, this is a function of this total power, right? Because your sum over sum of all this total pi star should be just equal to the total power, right?
That's right.
Yeah. So when you decrease this p here, you will lower the level, right? So maybe like if I decrease the power, now I have a level like that.
Okay.
Yeah.
And
Then this is the total power now. And then you have a different set of pi square, right? Because a different set of pi here, right? So now the p1 is still 0, like p2 is something like here, right?
so for the P1 is 0, it means that the P1 is already regardless from the discharge, something
Yeah,
like
P1 equal to 0, then it doesn't. Oh, okay, sorry, I miss log here. Log is all missing here. I have the log here. P1, if anything is 0, you just get log 1, right? That one is 0 anyway, right?
Yeah.
Of course, if you have no power there, you don't have any capacity there. Yeah.
okay.
So, but if we
So in this case, if we have like this over time, so P1 something like 0 and Pi P1 in here 0, so we just calculate for P2, P4.
no, I mean no, it doesn't matter. You still consider from 1. Just like if you have any pi star is equal to 0, this doesn't contribute to this sum, right?
Yes.
Yeah, that's it, right? It doesn't.
0. Yeah.
Yeah.
0 is log 0 is doesn't contribute to that.
Yeah, it doesn't contribute to this sum, right?
This means that the capacity is will be decreased if P1 is equal to 0. The capacity will be decreased.
That's a weird question you're asking. I'm not so sure what.
Yeah, because P1 don't have contribution on there, so the capacity will be decreased.
When you decrease the power, you expect the capacity will decrease. That's reasonable, right?
Yes.
When you decrease the power, of course the capacity will decrease. But the question here is like, what's the optimum capacity, right?
Yeah, that's right.
And the optimum capacity is that you need to first find the power allocation. And once you find the power allocation, you just substitute this power allocation into this formula, will give you the capacity.
Yeah.
And the power allocation is simply like a kind of a water filling, that kind of phenomenon. So it's very easy to find. So if you have, of course, we just show a discrete case, but in general, I draw here like a continuous case. It will still hold basically the conclusion. So like here, I have a band here that something like this. I'm going to try to efficiently use this band. So the best thing I can do is I just say, let's say the total power will be that much, meaning that like this is the total power. Then I will basically like not going to use the first set of bands here, right? This is basically, these bands will be useless. Here, for example, like at this particular band, the amount of power I'm going to use is just like this height here, right? And then the total capacity will be just whatever this height here, P1, P2, and so on, and then I just put this back to this formula to find the capacity.
To maximize that capacity. That's right.
Yes. Actually, maybe I was so maybe take this as an example. So this is a very simple case where I only have 1, 2, 3, 4, 5, right? Five different kind of like parallel channel here.
Noise.
Let me use maybe another color. Right, 1, 2, 3, 4, 5 here. pi channel here. So use this example. Let's say the what's this? This is a one allocation. Let's see, like the power P1 is 0 here, right? P2 is equal to 0.3, P3 is 0.6 here, P4 0, 0, P5 0, and this is another allocation, like P1 0 here, P2 is 0.8, 0. Something like that, right? And that's another allocation. When you continue to increase the power, now P1 is also non-zero now. Right? At the beginning, like only P2 and P3 are non-zero. When you increase the water level, like now P2, P3, and P4 are all non-zero. And you look at like what's the total power here is like 0.9, right? This is total power is 0.9 here. The total power here is like 1.4 plus 0.8, 2.2 here, right? And the total power is like 3.8 here, let's say. And then with this, you can compute the capacity, right? And the capacity will be like 1/2 log. In the first case, will be like 1/2 log P2. Let's just declare the P1 now, because it's equal to 0 anyway. It's like 0.3 over, I don't know what's the power here, but let's go back to here. Let's say at the beginning here, the power capacity will be like equal to 1/2 log P2 is 0.3 over whatever sigma 2 square, right? I have a 1 plus here, plus 1/2 log 1 plus 0.6 over sigma 3 square, something like that. So okay, that's basically what.
So what is the optimal? What is the optimal on that?
Okay. What are you talking about? Like, what's the?
I mean, that from that option, what is the most optimal?
We already what should I say?
We already have that, and then continue to calculate for.
No. What do you mean that was the most optimal? Like, you mean that was the optimal power?
Optimum
P?
capacity.
Oh, this is the optimal capacity for this P. P is equal to 0.9, right?
If we compare to another option, another scenario, that we
if you have, like, let's say when P equal to 0.9 here, you can have a different allocation, right? For example, I can have like not P is equal to 0.3 here. Maybe I can have like P1 is equal to 0.1, P2 is equal to 0.2 here, and this keep the same, right?
Yes.
Also P is equal to 0.9, but you can just put into our calculator, and this will be like have a smaller capacity than this capacity here. Yeah, this is the optimal capacity for this power. So so that's the basically the end. I like to talk about channel capacity, the proof of the kind of like for the channel coding theorem, and also the some kind of example like of some channels. So I will move into a different topic now. So we will start a new topic today. So I guess I go back to this journal here. So I just start a new page here. So I need to go back to the first page here. So what we're going to talk about is we're going to talk about something called method of type. So this is kind of extension of like the typicality or like the AEP asymptotic equipartition that we talked about several lectures ago. So the idea is that if you remember, like let's say if we have a discrete memory source, or if you think of like if we have like simply a mechanism that will generate some random number. For example, I have a random sequence. Let's say I have someone flipping a coin, like either getting a head or tail, and so on. And we want to ask like what are the sequence, what kind of sequence we can draw from this kind of like mechanism or from this discrete memory source. And if you remember previously, like we say everything we draw from the source will be typical, right? Typical in the sense that like it will have probability very close to like 2 to n matrix. This is the stuff 2 to minus n matrix, by the way. There's something like what we mean by typical. But what we are interested in here is like, how about we want to analyze other cases. So because when we talk about typical sequences, so all the analysis rely on the fact that we are assuming anything we draw from that source will be typical, basically. So how about like for the cases that actually we draw something that's not typical? So we'll use this called like method of types to kind of analyze that. The idea is that like we'll basically have a final differentiation of different sequences into different types. So we have a particular type, it's like those typical sequences, but we also have other types that will be not typical. So and we can like discuss and also like try to evaluate like what is the probability to have a sequence of a particular type, and that types can be non-typical. And of course, that probability, as you will see or we already known from our discussion in typical sequences, goes to 0 as n goes to infinity. So therefore, like those probability always have something like exponent 2 to n minus n something, and that something will be bigger than 0. So therefore, like as n goes to infinity, it will go to 0. Yeah, but that can actually discuss something pretty interesting. Actually, I give you some motivation here. So let's say I have a question like this. This is like pretty long. Actually this is like I like to talk about this earlier. I think because I push it very much near the end, because I think this is actually one of the information theory result that is kind of interesting, that can answer some question that's pretty non-trivial, that you may not know, and you don't know how to answer that. Like if you don't know this kind of like kind of result. For example, like let's say if I have someone like Tom, like he's going to throw a dice like 10,000 times, let's say. And let's say it's going to add up all the value. So let's say the dice is unbiased. So then I have probability that like have 1 is like 1 6, 2 is like 1 6, and so on, right? 1 2 3 4 5 6 is all equal to 1 6, right? So now if I ask you like what do you expect the sum of this 100, or like this average, or now let's say the sum of like this 10,000 kind of values here, the sum will be kind of approximately equal to like 10,000 expected the value of the dice outcome, right? Let's say the dice outcome, they call it x here. So this would be like something like 1, 6 times 1, 2, 3, 4, 5, 6, right?
To find what?
I mean, to find the total, let's say, if I fold the dice like 10,000 times,
Yes, 10,000.
what do you expect the total sum will be? The total sum will be like kind of like equal to 10,000 times the expected value of each time you fold the dice, right?
Yes,
And that would be like just like 1/6 plus 2/6 plus 3/6 and so on, right? And this would be just what?
No.
The 7 times 3, right? Yeah. This is a 21/6, right? Something like that. Yeah. So this is a 21/6 is what? That's a 2. That's a 3.5, right? So the expected value is kind of like 35,000, right? You expect that if you have someone like fold the dice like 10,000 times, he should approximately, according to what we discussed in typical sequences and so on, you expect that like he is going to get like 35,000, right? Now, but let's say there's a very small chance, and also let's say assume that Tom has an infinite amount of time, so he just keep following the dice 10,000 times, many times, until he gets something like more than 40,000. So we know that this is unlikely to happen, right? But yeah, if he fold it one time, he didn't get it, he just keep following it, right? Let's say the first time he got like 36,000, and then he was not happy, he fold it again, and then he got 35,000, he's not happy, he fold it again, until at one time that he got something like the total is more than 40,000. So now I ask you, like, when that happened, how many 1 do you expect in that sequence? I mean, like, if he fold the dice like 10,000 times, I mean, that's one point that he got the sum, the total sum is more than 40,000. And I will claim I'm kind of like a magician. Then I claim that I will, under that situation, I can bet on approximately how many 1s do I have in that 10,000.
Why is only 35,000? I think it's more than that.
What, 45,000? This is a...
That is more than that.
No, the total.
The total, 1, 2, 3, and until 10,000 will be more than that. Is this right or not?
What, okay, I got confused at what you're talking about.
I mean that why we should divide by 6 in here, because this will be there is no dividing by 6, no need to divide.
No, of course you have to divide by 6, right? That's the expected value, like each time you fold that, like on average your value will be 3.5, but sometimes you get a 1, sometimes you get a 2, sometimes you get a 3.
Yes.
And each time like if the dice is unbiased, then the probability to get a 1 is 1/6, get a 2 also 1/6, get a 3 also 1/6, 4 is also 1/6, right?
So I think that we want to sum all of that, sum of the outcomes.
That this expectation x is just like px times x, right? And sum for x.
What in here is a sum of all of we got, or the probability in here?
No, that's probability. This is the expectation here. Is this one here, right? Is the probability. Let's say let me let me use x anyway. So this x here will be like 1, 2, 3, 4, 5, 6, right?
Yes, that's right.
Probability of 1 is like 1/6, 2 is 1/6. This is the expectation, right?
That's
This is basically a definition of expectation, right?
That's right.
What's the expected value you throw a dice will be px times x and sum over that, right?
Yes.
P6 is equal to 1, 6, like for each of this value here. X here is equal to 1, 2, 3, 4, 5, 6, right? So that give you here, right?
Oh. So what actually what is it? What is it? What do you want to say here?
This is the total sum after 10,000 fold, right? So yeah, anyway. Right, you 10,000 times. So on average, you expect that like you get something like 35,000, and also like when you fold many times, then we'll, by law of large number and our discussion with typical sequences, we'll get closer and closer to the average, right? So we're closer and closer to this the expectation like 3.5, or like close to this value 45,000 here. But as I said, like if this Tom here doing this like task of like folding these dice, if he just have like so much time, he just keep doing that until like he gets something like more than 40,000, let's say, right? Then for that particular sequence that he flown, that have that result in like the sum larger than 40,000, I can ask like what's the number of 1, or like basically what I want to show is that I will be able to predict how many 1 and how many 2, how many 3, and so on in that particular sequence. Yeah. And this is kind of like, I would say, pretty non-trivial. Like, I would say it's unlikely you know how to solve it. Like with like, kind of, if you just take a class in like elementary probability and you know how to find the result for this one. Yeah, so this is the part. I think it's pretty interesting. Therefore, so we're trying to answer this question later on, like maybe today or like maybe
how many
this class.
What is it? How many
No, 1 or 2 or 3.
How many?
Because you fold 10,000 times, right? You may have like 3,000 of 2 or like 1. On average, that would be like just 1/6 of 10,000, right?
That's right.
But if you have 1/6 of 10,000 of 1, 1/6 of 10,000 of 2, and so on, you won't get 40,000, right? You get like 35,000, right?
Yeah.
Definitely, you don't really have like 1/6 of them 2, 1/6 of them 1, and so on. You have a different distribution. Yeah. But the question then is that what will be that distribution? Huh? Wait, well, let me. So, do you get what I'm saying here? Like, when I fold it like 10,000 times, I may have a sequence 1, 2, 1, 2, 1, 1, 2, 3, 4, or let's say don't say 10,000 times, maybe just 10 times, right? Then I will have a sequence that, let's say like this, right? 2, 3, let's say. This is like, right? Then I can ask like how many ones in that sequence, right? In this case, I have like 1, 2, 3, 4, and 4 ones here, right?
Yes, that's right.
Yeah, that's my question. And if you have like 10, of course, like if you only have 10 times, you may get a sequence like that. But if you have like 10,000 times following that, you know that you have a, right? You have like pretty high likelihood that like you have 1/6 of them are 1, 1/6 of them. But then like if you have 1/6 of them are 1, 1/6 of them are 2, 1/6 of them are 3, and so on, you won't result in like 40,000 of them, right? Of course, like you will result 45,000 of them, right? Yeah. So that's what I meant. Like, if that guy he fold those dice, he's just not happy until he get like 40,000 of them, and he eventually get it. Of course, he will probably need to repeat many times until he get it. But let's say eventually he get it. If he eventually get it, then I know that definitely that shouldn't be like 1/6 of them or 1/6 of them or 2 and so on, right?
Yeah.
But then like what is that? Like how many 1 do I have actually? How many 2 do I have and so on?
How many 1 you have? Will be 1/6.
No, you cannot, right?
I cannot.
Of course you cannot, because I want to say that like he got the sequence that eventually the total sum is bigger than 40,000.
Should be biased.
No, it's not biased, but it just can happen, right? That's the whole point. Like we talk about this method of type is as an extension of typical sequences. When we talk about typical sequences, we say everything we pull out will be typical. So therefore, eventually saying that like everything we pull out will have like sum is equal to 35,000, because like every sequences we pull out will be approximately have 1/6 of 1, 1/6 of 2, 1/6 of 3, and so on. But everything is probabilistic, right? There's still chance as you go through the homework. There's still chance.
Yeah.
Although it's very small, that you can get something that's not typical, right?
Yeah.
And there's a chance that you will get a sequence actually is not typical, and we have like not 1/6 of 1, 1/6 of 2. So there's a chance that like, you're actually able to get a sequence with the sum more than 40,000. So then a question is like, or like actually probably a pretty, on the surface it looks like a pretty magical, like how I'm able to answer that. It's like I'll just claim if that actually happened, then I can predict like how many 1, like how many 5, how many 2, and so on in the sequence. And that definitely won't be 1/6, right? If they are 1/6, you get 35,000, but they won't be 1/6. Yes.
More than that, more than 1.
Actually, 1 will be less, right? The smaller values will be less,
Yeah.
and then the larger values will be more.
Yeah,
But how much?
Like last time you said in the previous class.
I forgot actually. Yeah.
Maybe we should write where is the most and where is the highest to get that probability. Make some histogram. I mean that for how many for 6, how many for 5, how many for 4, until how many for 1, and sum for all of them.
You can, how can you do that? Like here, like you have very little information, right? The whole point is like you don't have the distribution. You know the original distribution is like unbiased, right?
Yeah, unbiased.
But you know that like given that is like larger than 40,000, the empirical distribution in terms of like how many 1, how many 2, and so on, definitely it's not uniform, right?
Yeah.
But I think like from whatever we discussed in the past, we didn't describe like how we are able to know that distribution, right? Unless you have the distribution, you can draw some histogram and so on. But here you don't know the distribution, right? So that we are going to talk about here actually. Yes. So I guess it's kind of clear what we want to.
Interesting.
Yeah, it's actually interesting. Something pretty interesting. So.
Thank you.
Yes.
So what the principle? I mean, what the concept for that?
The concept, like as you will see later on, is like we are going to when we talk about the typical sequences, we only have one type. So it's like something is typical, other things non-typical, and then for everything non-typical, we don't care about it. So when we have this so-called method of type, we have a type class is typical, but then we also like kind of have a final kind of distinction of like the non-typical sequences. So we separate them into different types. The types is essentially just like the empirical distribution is one type, actually. So in the sense that like I'm jumping ahead here, but a type of sequences will be like if I have one particular type here, the typical sequences will be like 1/6 of 1, 1/6 of 2, 1/6 of 3, 1/6 of 4, and so on. This is one type that's typical. But I can have another type. Maybe I have like 1/12 of 1, 1/12 of 2. Then I have like 1. I'm not sure. I can add up 1 here. Let me be careful.
It's not uniform then.
No, it's not uniform.
Yeah. Therefore, he already discharged the uniformly.
Wait. You need to be careful. Your dice can be unbiased, but you pull out a sequence does not necessarily always be uniform, right? There's when that sequence is very long, there's a very high chance that that sequence will be uniform.
Yes, of course.
But there's also a chance, because everything is probabilistic, right? There's also a chance that like the sequence you pull is not uniform, right? Although the probability is now very small. So actually, that's a.
But that probability is really small.
Yes, that's the whole point. That probability is really small. So therefore, when asked this question, I say like, I will assume this guy have like infinite amount of time. So he for this one time it doesn't work out, or another time so maybe like for until the end of the universe, eventually he gets something like this. But then like, yeah, but then that is possible to happen actually.
And that will be possible.
Yeah, everything the probability is larger than 1 is possible. Oh, sorry, larger than 0 is
because
possible, right?
Is unbiased. How? Yeah, it's really small probability.
Yeah, it's small probability. You see that it's small. Yeah, it's really small, but it doesn't mean that like it's equal to 0.
Yeah, that's right. Yeah, that's right. Even small, there is probability.
So actually, yeah. So maybe let me let's see. Let me use a coin tossing as example again. Like if I toss a coin, let's say a let's say I have a bias coin. So let me maybe start with a new page here. Let's say I have a bias coin of coin here. There's a bias. The probability of head is equal to, let's say, 0. Let's say head is 0.6, and then so therefore probability tail is 0.4 here. So let's say I toss it like 1,000 times, just 1,000 times. So in this case, like the typical one will be like I will approximately get like 600 head and like 400 tail, right? And the probability to get one of those sequence is just like 0.6, or like particular sequence that have like a 600 head and 400 tail will be like 0.4 times 400, right? So for example, like if I have a sequence that have like first have 600 head followed by like 400 tail, and then particular sequence of probability will be just like that, right?
Yes, sir.
And I'm actually like, if we look at that, what is this one here? This is actually equal to, I can write it as a, let's see.
Very small.
Yeah, it is small. I can write this as a, let's see.
1 means 0.6.
No, I want to put it like this form. I want to like put it like this kind of 2 to log something form. 2 log this 0.6, 600, 0.4, 400. So then therefore it's like 2, I have like 600 log 0.6 plus 400 log 0.4, right? Then I can write like put 1,000 here. Maybe I even put a minus sign here. I have like become 0.6 minus log 0.6 minus 0.4 log 0.4, right? And this is just the entropy. If we go back like what we actually familiar with, like we know this is one of the typical sequence, right? So therefore like exactly typical one. So actually this is exactly equal to 2 to minus NHX, actually the probability. Now let's look at like another sequence. Let's say that doesn't actually have like, that is basically not typical. This doesn't have say 600 head and 400 tail. Let's say I have another sequence have like, let's say 400 head followed by 600 tail. So this one is very unlikely. As you know, this one is very unlikely, but okay. But if you in terms of probability, it's also very simple, right? This one is like just 0.6 400 times 0.4 600, right? Yeah. And I can do the same thing here. Right? It's equal to 2 log this is 0.6 400 0.4 600. Now I can write this as 2 400 log 0.6 plus 600 log 0.4. Yes, yeah, yes. And then I do the similar thing, like pull like 1000 minus 1000 out. Then I have like 0.4 log 0.6. Oh yeah, minus 0.6 log 0.4. Now this doesn't look good to us, but what I can do is let me write this as 10,000 minus 0.4. Let's see. Log 0.4 minus, or maybe plus, log, or maybe I should put minus log 0.4 0.6. Okay, this is nothing, right? When I have like,
how you experiment?
No, this one, this term here, I still have one more term, like 0.6 log 0.6 minus log 0.6 0.4. Right, this is this is kind of silly, right? 0.6 I write it at like 0.4 minus log 0.4 over 0.6.
How do you do it?
The 0.4 got cancelled.
From this one, how it could be like this?
Your log here, log minus log something is equal to log 0.4 over this guy, over 0.4 0.6, right?
Yeah, that's right.
So therefore it's not 0.6 here.
Okay, that's right.
Yes. But then if I white light this, actually I can group the terms, right? So then I have minus 10,000 minus log 0.4 log 0.4 minus 0.6 log 0.6. Basically I have these two terms, I come to here. Then I have some positive terms here, like I have minus, I have positive now. 0.4 log 0.4 over 0.6 plus 0.6 log 0.6 over 0.4.
That can use TL.
Yes, exactly, that's the KL. So this one is just the entropy, right? Yeah. That's the entropy of the original distribution. Right, that's the entropy of the source, like HX here. But this part is here is actually the KL divergence. KL divergence between what? Between the or maybe I'll just write it this way, between 0.4, 0.6. 0.4, 0.6 is the empirical distribution of the sequence. I have, let's see, is that, yeah, I have like kind of like approximately 0.4 of the sequence, 0.4 ratio of the sequence is head, and 0.6 fraction is a tail. And with the original distribution, this is original. So, okay, anyway, maybe I will just stop here, then we will come back. I'll take a break for 15 minutes, and I will come back. So, but yeah, this.
Yeah, that's same. It's just only there is KL on there.
But then you see that, okay, I have the original probability is small.
Yeah.
Like it's a -2 NHX. This is even smaller. I have 2 to the minus NHX, but I have something like extra terms here. It's the KL divergence between.
More smaller.
Yeah, yes, between the original source and the final source. So okay, I will take a break for 15 minutes and we'll come back.
Tom,